Hello, and welcome back to my YouTube channel. My name is Professor Kavala, and today I'm going to be talking to you about the continuous time Fourier transform, where this topic is very important in the realm of mathematics and engineering. And in this video, we're going to break down the derivation of this inverse Fourier transform and this Fourier transform here, and really see how we get to these equations, where the goal of the video is to analyze and represent continuous time domain signals such as x of t in the frequency domain x of omega. And the reason is, in the time domain, we tend to have to use calculus, versus in the frequency domain, we tend to have to use algebra, and algebra becomes easier to manipulate and work with than calculus. So we map to this algebraic domain, we do our calculations there, and then we map back to the calculus domain or the time domain. So in order to explain the continuous time Fourier transform clearly, I'm going to take two examples, and I'm going to analyze these two examples in order to generate these two equations here. So for my first example, let me call it example number 1. And let's say that 1a says that given an A periodic signal, x of t, again, you can imagine this x of t to be like a song. So for example, a song that never repeats. So again, let x of t be an aperiodic signal. So I'm just going to draw a quick aperiodic signal here. And I'm going to say then that imagine, right, from negative t over 2 to this t over 2, we get a signal that looks like this. But then the signal does not repeat itself, right? So afterwards, it looks kind of like that. So again, basically a song that never repeats itself, right? So we can call this here an A periodic signal, or we can call this a non-periodic signal. I hope this makes sense. Again, this is a building block to really understand on a fundamental level what the Fourier transform is trying to tell you. Okay, so now let's move on to 1b. And 1b tells us that, okay, given this aperiodic signal, let's take a window function. All right, so let's take a window function, where this window function, call it x capital T of t, is equals to x of t minus t over 2 to t over 2, and then 0 otherwise. So what does that look like? So what I can say is that x of capital T of t with respect to t, I can say then that let's take from minus t over 2 to t over 2. And again, we can repeat that function. Again, this might not be up to scale because I'm drawing this by hand. But essentially, it takes that function from minus t over 2 to t over 2, and then elsewhere it's just 0. All right, so we've basically taken, we call this a window function of our A periodic signal. And again, understanding this is a fundamental to the continuous time Fourier transform. The last part of example 1, let me call it 1c, tells us to create a repeating function. So if you create a repeating function, and let me call this repeating function x tilde of t, where it is equals to x capital T of t, so my window function for minus t over 2 up until t is t over 2, and also x tilde of t is equated to x tilde of t plus n capital T. And this is for when n is equated to any integer other than 0. So essentially n is equated to dot 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 minus 2 minus 1 1 2 dot dot dot. And again, keep in mind this here is going to be a repeating function. So let me go ahead and show that. So let me just bring this down just a little bit because I want to keep the entire thing on the screen. So what we're looking at here, to satisfy this first condition here, we take from minus t over 2 all the way to t over 2, and we have our same function. And as you can see, this first condition here is when n is equated to 0. So basically, if n is equals to 0, this just becomes this here. So then it's just x of t, which is why we don't include the n is equals to 0 here. So then to satisfy this second condition here, let's take two examples when n is equals to 1 and n is equals to negative 1. When n is equals to 1, we're going to basically shift x of capital T of t by a factor of capital T. So this means that if when n is equals to 0, we were here. So when n is equals to 1, we're going to be at capital T. So then our next marker is going to be at minus 3t over 2, and we're going to get our same function, something like this. And for n is equals to negative 1, it's going to shift to the right. So it's going to be, so this is negative t, it's going to be regular t. And then it's going to be 3t over 2. And we're going to get our same function here, something like this. And this continues on both sides. Please take a moment to pause the video and really understand what is going on. Again, remember, our first step is to take any periodic signal, such as a song or any type of music or the waves that is not periodic. It doesn't repeat itself. And then we break it into a window function. We just take one snippet of that song, right? We take one snippet and then we repeat that snippet over and over. So now we create a repeating function. And so that's a third part of this example number 1. And just so we understand where we're going to with this example number 1 is going to build on top of another example, which I'll do next. And then we're going to conclude some things and then figure out our final solutions, which will be the Continuous-Time Fourier Transform equations. I hope this makes sense. If you have any questions, please leave them down in the comment section below, and I'll be sure to get back to you. Okay, so the next thing we're going to analyze is what I call the example number 2. And there's only two things to note for this example. And the first one I'm going to call 2a. And I'm going to say that the limit as t goes to infinity of our window function x of capital T of t is equated to our aperiodic signal a of t. And essentially what this is saying is that the bigger the window size, the closer it is to our regular function or our regular aperiodic signal a of t. And to really see this clearly, I'm going to do what I call a visual representation. And this is part of the example. So again, consider this aperiodic signal x of t. And what I'll do is I'll change its structure. I will say then that it looks like this. All right, where this here is minus infinity and this here is infinity. Now, a signal like this can be thought of as like white noise. So white noise never repeats itself. It just keeps going. It's not periodic. Another example of a signal like this that just keeps on going like this forever and ever and never repeats itself would be, for example, ocean waves or river waves. Essentially, they're never repetitive. They're always different. Imagine you take that type of signal that never repeats itself from negative infinity until infinity, or the beginning of time to the end of time. And what we're going to do is we're going to take a window of this function and say that now the limit as t goes to infinity of x of capital T of t of our window function is basically equated to x of t, which is just our regular aperiodic signal. And this makes sense, right? Because we say that essentially this function is going to be my entire signal from negative infinity to infinity. And again, it looks like this. Now, the second part of my example 2, let me call it 2b, says that if I then take the limit as t goes to infinity of my x tilde of t, so my repeating function, I will also get x of t. And this makes sense, right? Because since the window itself is equated to x of t, that means that the repeating signal will essentially just be the original signal x of t. And so now a visual representation of the repeating function is essentially says that the limit as t goes to infinity of x tilde of t is equated to x of t. So that means that if I have my function here, where this is t, it's essentially going to be my starting function from infinity to minus infinity. So now where are we going with these two examples, right? Because it's very important to understand the flow of the work. So the first thing is example 1 tells us that if we have this x of t, we can cut it into this window function x of capital T of t, and then repeat x of t to give us x tilde of t. And example number 2 tells us that if we then take the limit as t goes to infinity of both these functions, we can essentially simply just get our original signal x of t. And that's basically what the fundamentals of the continuous time Fourier transform is telling you. So now let's go ahead and see how this all can come into fruition and write down clean-cut equations. Okay, so then to begin, from example number 1, we clearly said that we have a repeating function x tilde of t, which is equated to x capital T of t, our window function, for minus capital T over 2 to capital T over 2. And we have x tilde of t is equated to x capital T of t plus n capital T, where n is equated to ... minus 2 minus 1 1 2 ... where again this here is my n is equals to 0 condition. So now since this here is a repeating function, we can go ahead and use something we've studied in our past videos called the Fourier series. So I can say then that we can say that x tilde of t is equated to the sum of k is equals to minus infinity to infinity, a k e to the j k omega naught t. Let me call this my equation number 1, where again from our Fourier series video, we know that ak is equated to this 1 over t integral from minus t over 2 to t over 2, x tilde of t e to the minus j k omega naught t dt. Again, I just want to point out that the fundamental frequency omega naught is equated to 2 pi over my period t. So then to continue analysis, we can say that since x tilde of t is equated to x capital T of t, or this window function, in this range minus t over 2 to t over 2, we can essentially just replace this x tilde of t with this window function here. So what that looks like is I can say that ak is equals to 1 over t. My integral from minus t over 2 to t over 2 stays, but x tilde of t is essentially just this value here, right? So x capital T of t e to the minus j k omega naught t dt. I hope this switch makes sense. And again, it's because I'm taking the integral within this range here. Next observation I can do is I can say that since x capital T, or my window function, is equated to 0 for t less than minus t over 2 and t greater or equals to t over 2, right? Basically, x capital T, or my window function, is 0 for t outside of this range. We can change ak is equals to 1 over t from negative infinity to infinity and still keep our window function here. So I hope that makes sense. And essentially, this switch from our repeating function to our window function, and then changing our parameters from negative t over 2 to t over 2 to negative infinity to infinity. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. Now, let me go ahead and call this equation number 2. And let me say I'm going to sub 2 into equation 1 up here. So if we go ahead and sub in equation 2 into equation 1, we get that my repeating function x tilde of t is equated to this sum of k is equals to minus infinity to infinity. Ak is this 1 over t integrated minus infinity to infinity x of t of tau e to the minus jk omega naught tau d tau, and then e to the jk omega naught t. Where essentially, I don't want to dive too much into this replacement or change in variable tau, but essentially this is what you call your integration time, or the time that you have to plug in and get a solution for. And then this t here is going to be your observation time, so the real time that is passing currently. So now let's go ahead and plug in this omega naught is equals to 2 pi over t, or essentially saying that 1 over t is equated to omega naught over 2 pi. So then we get that my repeating signal is going to be equated to the sum as k is equals to negative infinity to infinity times omega naught over 2 pi integrated from negative infinity to infinity, my window function x of capital T of tau e to the minus j k omega naught tau d tau e to the minus j k omega naught t. Let me go ahead and move this omega to the front here and move this 2 pi to the front here. So then I get x tilde of t is equated to 1 over 2 pi. The sum as k is equals to minus infinity to infinity times integrated negative infinity to infinity. My window function x of t of tau e to the minus jk omega naught tau d tau e to the minus jk omega naught t times omega naught. So now hopefully we can see what we need to do to this equation to get x of t. And essentially what we need to do from our example number 2 that we studied is say then that x of t is equals to the limit as t goes to infinity of our repeating function x tilde of t. Therefore, I can say then that x of t is equated to the limit as t goes to infinity of 1 over 2 pi, the sum as k is equals to minus infinity to infinity, times the integration of minus infinity to infinity x of my x capital T of tau, or my window function e to the minus jk omega naught tau d tau e to the minus jk omega naught t omega naught. And now, other than doing some cleanup, which I'll do on the next page, this here is a good representation of your inverse Fourier transform, where this internal here is going to be your Fourier transform, x of omega. Okay, so now on the next page, I'm going to clean this up so that we get a nice equation for the inverse Fourier transform and the Fourier transform. So now in order to simplify this equation here and make it nice and clean, we want to do some observations. And the first observation I'm going to say is that omega naught is equated to 2 pi over t. So that means that if we take the limit as t goes to infinity, this means that we're taking the limit as omega naught goes to 0. And just as a quick example to clarify this, consider if my t or my time is equals to 2 seconds, or it takes me 2 seconds to do a task, my frequency is going to be 1 over 2 hertz. And my omega, or my angular frequency, is going to be 2 pi over 2, which is just pi. But then if it takes me longer to do a task, let's say 4 seconds, and every 4 seconds I keep doing that task, so periodically it's 4 seconds, my frequency will be 1 over 4 hertz. As a result, my angular frequency will be pi over 2 radians per second. And as you can see, as I increase my time from 2 to 4, it's getting bigger, my omega is getting smaller from pi to pi over 2. So I hope this first observation makes sense. And this observation number 1 also tells us two things: that as my t goes to infinity, the frequency spacing omega naught becomes infinitesimally small. So omega naught gets to this d omega, and the discrete frequency, so k of omega naught, becomes the continuous frequency variable. So it just becomes omega. So for my first observation, as we take the limit as t goes to infinity, omega naught, or my frequency spacing, becomes this very small delta omega, and my discrete frequencies k of omega naught simply just becomes a continuous frequency omega. The second observation we want to consider is that from my example number 2, as t goes to infinity, my window function x of capital T of tau goes to this x of tau, which is my original aperiodic signal. And again, we proved this in the example number 2. And lastly, the third observation is, since the spacing is now extremely small, so this d of omega, or delta omega, we can use what we consider the Riemann sum. And again, this is a calculus 1 type of topic, which says that if we sum up an infinite number of infinitely thin slices, the sum naturally evolves into an integral. So essentially, Riemann sum says that the sum as k is equals to negative infinity to infinity dot 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 of this omega naught. And when we sum up an infinite number of infinitely thin slices of omega naught, this maps to the integral from negative infinity to infinity of this infinitesimally small delta omega. So now what we can do is work with these 3 observations here to simplify this equation. And what I can do is, according to my first observation, for the limit as t goes to infinity, omega naught changes into this delta omega. So this omega naught here will be this d omega. And my discrete frequencies turn into a continuous frequency, where again here will just be omega, and here will just be omega. And again, this is because I'm taking the limit as t goes to infinity. From my second observation, as t goes into infinity, this window function becomes the aperiodic function. So this term here just turns into my x of tau. And last but not least, since I'm summing up an infinite number of infinitely small slices, this summation becomes an integral from negative infinity to infinity. And that is my third condition, or my Riemann sum. So therefore, we can write these two nice clean equations where I can say that x of t is equated to 1 over 2 pi integrated from negative infinity to infinity x of omega e to the j omega t delta omega, or change in omega, where capital X of omega is equated to the integral from negative infinity to infinity x of t e to the minus j omega t dt, where again this here is your inverse Fourier transform equation, and this here is your Fourier transform equation. And again, just to be clear and non-ambiguous, the idea behind the Fourier transform again is to represent an aperiodic function, so this x of t, in terms of complex sinusoids at all frequencies, this x of omega. And that's because in the time domain, we're dealing with calculus most of the time, while in the frequency domain, we're dealing with algebraic type equations. In the next video, I'm going to be doing some examples of the continuous time Fourier transforms, so please make sure to look out for those. If you have any concerns about any of the topics talked about in this video, please leave your concerns down in the comment section below, and I'll be sure to get back to you. If you liked the video, please give it a thumbs up, and please share the video to your colleagues and friends so they can also obtain the knowledge. And if you like what the YouTube channel is providing, please consider subscribing to the channel. It really helps the algorithm. Thank you.